Welcome to today's Explainer. Today, we are taking a fascinating look right under the hood. If you're looking to master the mechanics and the essential vocabulary of how a vehicle manages heat, well, you are in the exact right place. We're going to treat this as a definitive study guide. It's perfectly structured to help you lock in these technical concepts and terminology for good. So let's just dive right in and decode one of the most absolutely vital systems in any motor vehicle, the engine cooling system. To kick things off, consider this question. What happens to most of the energy in petrol when an engine runs? Now, you might logically think, well, it all goes into turning the wheels and making the car move forward, right? But surprisingly, the vast majority of that energy is actually converted directly into heat. Internal combustion engines produce power by burning fuel, and that explosion creates tremendous heat and pressure. We're talking about an immense amount of thermal energy that simply can't be entirely converted into mechanical power. And honestly, if left unmanaged, all that trapped heat would be catastrophic. To help you memorize this effectively, we've broken our study guide down into 5 logical steps: the importance of cooling, the 3 main functions, system components, the fluid's path, and common causes of failure. Okay, section 1, the importance of cooling. Before we look at the parts themselves, we really need to understand the fundamental why. Temperature control is actually this highly delicate balancing act. It's kind of like a Goldilocks situation. You might think an engine should just be kept as cold as humanly possible, but actually, when an engine runs cold, the internal components wear out much faster. A cold engine is way less efficient, and it pumps a lot more pollution into the atmosphere. On the complete other end of the spectrum, an overheated engine will suffer from warped metal and literally destroy its own operating components. So the cooling system isn't just a giant ice pack for the engine. It's a precision temperature regulator keeping things safely away from both of those destructive extremes. When you pop the hood of most modern cars, you're going to see a complex network of hoses and pressurized caps. Now, air cooling definitely exists. You'll still see it making engines lighter in a few specific cars and most motorcycles, but the vast majority of motor vehicles today feature closed liquid cooling systems. That specific network of hoses, pressurized caps, and fluid is exactly what we are focusing our study guide on today. Moving on to section 2, the 3 main functions. Get your pens ready, because the cooling system has a highly specific job description. It can be perfectly distilled into 3 fundamental rules. First, it must remove excess heat from the engine to prevent a total meltdown. Second, it must maintain the engine at an operating temperature where it works most efficiently. And third, and this actually surprises a lot of people, it is responsible for bringing the engine up to that right operating temperature as quickly as possible when you first start the car. It actively helps the engine heat up fast so you don't suffer the mechanical wear of a cold engine. So, what exactly is that magic temperature? Generally speaking, an internal combustion engine hits its absolute sweet spot in the incredibly specific temperature range of 80 to 90 degrees Celsius. Let's look at how the physical parts are engineered to maintain this exact thermal window. Section 3, System Components. This is the anatomy portion. I want you to actively map these upcoming vocabulary words to their physical functions. First up is the water pump, sometimes called the coolant pump. Think of this as the beating heart of the entire system. It's physically responsible for pumping the coolant liquid through the engine and hoses. What's super fascinating is how it gets its power. The water pump uses rotational power directly from the engine's crankshaft and serpentine belt to literally force the coolant forward. Next, we have the radiator. This is your main heat dissipation zone. The radiator is basically a large heat exchanger that's strategically placed to transfer the excess heat from the engine directly out into the atmosphere. And to make sure there's always adequate airflow, especially when you're just sitting at a red light, it's aided by radiator fans. These fans increase the airflow across the radiator fins to help the system cool much more efficiently. Then we have the thermostat. Now, this isn't like the digital dial on your living room wall. This is a physical, thermostatically controlled valve. It acts as the ultimate gatekeeper, regulating the flow of the coolant. Remember how we said the engine needs to heat up quickly? Well, the thermostat stays closed when the engine is cold, trapping the fluid inside the engine block. It only opens up to allow flow to the radiator once that desired 80 to 90 degree operating temperature is finally reached. Working hand in hand with those mechanical parts is the CTS, or coolant temperature sensor. This right here is the brain of the operation. It constantly monitors the actual temperature of the engine. But it doesn't just watch, it takes action. The data from the CTS is used to electronically control those radiator fans we just talked about, turning them on and off as needed. Plus, it updates the temperature gauge right there on your dashboard, so you always know what's happening. And finally, we have the lifeblood of the whole setup, the coolant itself. This is a carefully formulated liquid, usually a very specific mixture of antifreeze and water. Its primary job is to act like a sponge and absorb heat while flowing through the engine. Why this specific mixture? Well, it has low viscosity and low density, so it flows easily. It also boasts chemical neutrality, meaning it absolutely will not corrode or eat away at the metal engine block. Plus, it's relatively harmless, low cost, and easy to find. Section 4, the fluid's path. Now that we have our vocabulary locked in, let's put all these components together into a working model. Let's trace a single drop of coolant. Step 1. The water pump aggressively circulates the coolant, forcing it deep into the engine. Step 2. The fluid travels through specially designed passages around the cylinders, known as the cylinder block and cylinder heads. As it passes through these violently hot areas where the fuel is literally exploding, the coolant absorbs and carries away all that intense, excess combustion heat. Step 3. The now overheated fluid reaches the thermostat valve. Because the fluid is hot, the thermostat valve opens wide up. Step 4. The fluid is routed directly out of the engine and straight into the radiator. Here, acting as a heat exchanger, the radiator releases that surplus heat out into the atmospheric air, aided by those fans. Once it's cooled down, the fluid loops right back to the water pump, and this pressurized cycle repeats endlessly while you drive. But what happens when this perfect cycle breaks down? That brings us to Section 5, common causes of failure. When the temperature gauge on your console spikes into the red zone, it's usually due to a few common culprits. The biggest reasons often revolve directly around the fluid itself. The simplest issue? Just having too little coolant in the system to absorb the heat. Another huge issue is a clog or obstruction inside those narrow engine passages or radiator tubes, which just stops the flow dead in its tracks. And of course, a fluid leak anywhere in those pressurized hoses will instantly compromise the entire system. Beyond the fluid, there are the mechanical failures. If you have a malfunctioning thermostat that gets stuck in the closed position, that hot fluid can never reach the radiator to cool down. A faulty radiator fan means there isn't enough airflow to pull the heat away when you're driving slowly. And a broken water pump, maybe due to a snapped serpentine belt, means the entire circulation process completely halts, leading to rapid, severe overheating. To truly cement this whole system in your memory, let's look at this direct quote from our source material, which beautifully summarizes the core thesis of everything we've learned today. As engines produce more heat than can be converted into power, a cooling system is required to control operating temperatures and prevent overheating. It is a completely non-negotiable requirement for the survival of the internal combustion engine. So, we've covered the crucial importance of temperature control, the main functions, the key components, the fluid's path, and exactly how it all can fail. Now I want to leave you with a provocative thought to apply your newly memorized knowledge to the real world. Knowing exactly how this delicate, highly pressurized system works, what is the most critical component you should go check under your own vehicle's hood today? Think about it, keep studying, and I really hope this explainer has completely demystified the engine cooling system for you.